So far, in our discussion on waveguides, we have come across two kinds of structures. One is the two conductor structure, that is a parallel plane waveguide, and the other is a rectangular waveguide which is made using a single conductor, which can also be thought of as two pairs of parallel waveguide conductors arranged in a vertical fashion. So our analysis of the waveguides, the two kinds of waveguides, even though the procedure was different, our aim was the same, that we would try to figure out what is the field or the fields inside the waveguide, and there could be some fields which are transverse to the direction of propagation, there could be some fields which are along the direction of propagation, so on and so forth. But all of this analysis involved a direct or indirect assumption of some kind of an intrinsic wave that is entering the structure and undergoing reflections. So after a point, we are really not concerned about the ways in which the wave is getting reflected, but more interested rather in the fields that are existing due to those reflections, and ultimately the fact that a wave is being guided along the direction of the length of the waveguide. So all said and done, it is nonetheless important for engineers, students, academics, researchers, and so on, that while we have solved for what the fields are, we know that there are some big expressions involving sine, cos, and whatever terms. It is very important to know what do these fields look like, or the question is, can we visualize the fields in some manner inside the waveguide? So let us slowly attempt to do this in today's lecture. Now, when I say trying to visualize, there is one thing that we know. Let us consider something as simple as a parallel plane waveguide. So in case of a parallel plane waveguide, we know that there is some kind of a incident wave on one of the conductors, and there is a reflected wave also. Now, depending on whether you are looking at the TE mode or the TM mode, say for example, if it is the TE mode, in that case the electric field would be in this direction and the magnetic field would look like this. So this is the way it would travel. But you know, this electric field is the electric field of the intrinsic wave. Now if you remember that if this is incident with an angle of theta, the reflected angle would also be theta. So what we said, that there will be some total field which exists because of these waves which are coming in and getting reflected. So in some sense, the incident wave and the reflected wave, they superimpose on each other and they create some new fields. But all said and done, these new fields are not merely the fields which are carried by the incident wave itself. But one thing we can say is that no matter what, we can actually take a look at the incident wave and say the fields will be aligned in what direction. So if you assume this is the z-axis, this is the positive x-axis, and this is the y-axis. So in that case, for TE mode, let us say TE some TE suffix small m, the electric field is always aligned along the y direction. So we'll have EY, and H is on the xz plane. So we will have Hx and Hz components. This we can say. Likewise, if the propagation is transverse magnetic, in that case what would happen is that this would be the H field and the electric field would look like this and the incidence would be something like this. So the H now would be along the y direction and the E would lie on the xz plane. So in case of Tm, we will have Hy, Ex and Ez. So this is what is there. We have even derived the expressions for both modes in few classes back. So let us say that this distance between the two plates is some d, and now let us do a little bit of revision. Let us do a little bit of revision and try to write down what are the field expressions for the Tm mode. So for the Tm suffix m mode, where m can be any non-negative number, non-negative integer so to speak, we have to write the expressions for Hy, Ex and Ez. So if you recall, we had derived the expressions for all of these. So let me just write them again for you. So Ex was something of this kind. 2j Ei0 times this times cos of m pi by d x times e raised to minus j beta z 1 minus m lambda by 2d the whole square. So we had actually proved that this m lambda by 2d is nothing but cos of theta. So what effectively happens is that m lambda by 2d is nothing but cos theta. So this quantity inside the root becomes sin theta. So now effectively what is happening is that we are getting this sin theta times cos of m pi by d x times e raised to minus j beta times sin theta times z, where we had said that beta sin theta is the effective phase constant of the wave that is being guided along the z direction. So what we can say, if beta is the intrinsic phase constant, then beta sin theta we can write them as beta prime, that is the effective guided wave phase constant. So therefore now what I can do very easily is that I can write this j as an e raised to j pi by 2, a phase term, which I can absorb it over here. So what I can do is I can say this is 2 e raised to j pi by 2 ei0. Now sin theta I can simply write as beta prime by beta, because beta sin theta is beta prime. The cos term will stay as it is, This I can write as beta prime times z. This we know, but we are now just writing it in a slightly different way. So what I can now do is I can take this term and combine it with this other complex exponential. So let's write that. So oops, I made a small mistake. There is no j term over here for ex. So this will not be there. So I can write this without j. I'm sorry, just be very careful of this. In the TM mode, the j is there only for the ez term. Alright, so ex would look just like this. So I can rewrite, let us say, the ex as 2ei0 beta prime by beta cos m pi by dx times e raised to minus j beta prime z. I think this is all that is there. Yes. So there is no j term. Just be a little careful of that. Don't make the mistake which I am making. But good thing I corrected myself. So now if I want to look at the variation of the ex field, I can actually look at the real part of this field and I can write that this field at any given point of time would be nothing but the real part of this whole expression. So that would come out to be these three, the first couple of products are real. Now all we need to do is take the real part of this complex exponential. So all that we need to do is just write it this way. So the real part of this would be a cos, that is cos of beta prime z. So now what I can do, beta prime is nothing but beta sine theta, that we know. So we can write a term called as lambda g, that is nothing but the effective wavelength of the wave that is being guided along the plus z direction. So this is nothing but 2 pi by beta prime, and that is 2 pi by beta sine theta. The reason I am saying it in terms of lambda g is that it will be easier for us to later represent these fields as a function of distance. So therefore I am replacing the terms inside with some distance term. So therefore this becomes 2ei0 beta prime by beta cos m pi by dx times cos of 2 pi z divided by lambda g, because beta prime is nothing but 2 pi by lambda g. Now let's go for the Ez term. The Ez will have a complex term. It will be 2j ei0 this times sine this is how the way it is. So what can I say? So just like how this term becomes equal to cos theta, we had seen that this term is nothing but cos theta. We can actually say that we can actually rewrite this expression in the following way. We can write this expression in the following way. We can also put this j as equal to e raised to j pi by 2 times ei0 and this term I can rewrite and represent it in the following form. Just by a simple arithmetic manipulation, I can say that this is nothing but pi by beta times d. Can I write this? Yes, I think I can write this. We have already seen the relationship between m lambda by 2d and beta, and that is the way I am writing it. So now the other thing will be sine m pi by d x times e raised to minus j beta prime z. So this I can now write by combining these two terms. That will be 2ei0 times e raised to minus j, these two terms will get added up, plus pi by 2. That's all there is. So now I can take the real part of this to see how the magnitude is varying, and that would be equal to this entire term and finally there will be j over here also. This will become for the cos. So I can rewrite this beta prime z in a similar way as this, and I can write it as beta prime z is nothing but 2 pi z by lambda g. So the real part of this complex number would be a cos term. And what is that? That is the cos of 2 pi z by lambda g minus pi by 2. So with this we have found out the way the magnitudes of the electric field components Ex and Ez would be. Now we have one last component left, and that is Hy. So very quickly let us write that. Hy is nothing but 2ei0 by eta cos m pi by d x and e raised to minus j beta prime z. Now I will not solve for this. You can very easily prove yourself that the real part of Hy, the real part of Hy would be something of this kind. It's very easy. We are looking at the TM mode. So Hy is the easiest expression. Again, I am representing beta prime using lambda g. So this is what it looks like. So with this, we have got how the fields are actually varying by taking the real parts of Ex, Ez and Hy. So now let us put some value of m. So let us say let m be equal to 1. So that means the mode which we are looking at is the TM1 mode in the parallel plane waveguide. Now, one thing to note that is common in all three expressions, Hy, Ex and Ez, is that all of these are functions of x and z only. There is no function of y. Yes, Hy exists along y, but it's a function of x and z. So I mean, we can actually look at what is the variation along the xz plane itself, and that will kind of give us the pretty clear picture. We really don't need to consider y. So now, if we have m equal to 1, then what would the field magnitudes be? So I can now write Ex is equal to 2ei0 beta by beta prime cos pi x by d. Now we know that m is 1, so the m now goes away. This times cos 2 pi z by lambda g. Likewise, Ez will be 2ei0 pi by beta d cos, sorry, it will be a sine term, pi x by d cos 2 pi z by lambda g minus pi by 2. And Hy, simply substitute m as 1, and that's all we need. That's 2i0 by eta cos pi x by d times cos of 2 pi z by lambda g. That's all there is. So let us try to now visualize what the fields will look like. So which field shall we start with? We have three fields, or rather 2 electric fields and 1 magnetic field component. So to make matters easy, let us start with the magnetic field component, because there is just one component of it. So and Hy, let's write it again, 2ei0 by eta cos pi x by d times cos 2 pi z by lambda g. So now let us draw the waveguide structure again. This is what the waveguide looks like. This is the plus z direction, and let us mark some point. Let this be z equal to 0. and this is the positive x-axis. Let us say this point is z equal to 0, and for the x-axis this is also x equal to 0, and here it is x equals d. And let us put a limit or the bound for the z-axis also. Let us say z equals the half wavelength. Now wavelength means what? It is lambda g by 2. That is the half of the guided wavelength. Alright. So what are we looking at? We are looking at Hy. That is the component of the magnetic field along the y direction. So y direction is always perpendicular to the plane of the paper. So therefore even this Hy would look something which is perpendicular to the plane of the paper. So now where will the Hy become maximum? Where will the Hy become maximum? Let us first consider the variation along the x-axis only, just as a special case. Let z be equal to 0. So if z becomes equal to 0, the second cos term becomes 1, and what we have left with is 2ei0 by eta, which is a constant, times cos pi x by d. So on this axis we just have this term, cos pi x by d. So when x is 0, there will be a maximum. When x is 0, the field will become maximum. So that's like saying when x is equal to 0, this cos term will become 1, and ei0, this term, if it is positive, then effectively the Hy would also be a positive quantity. So therefore, since it's maximum, let us mark it with an arrow that is coming out of the plane of the paper, and let us make a big circle. Let us have a convention that how big the circle is indicates the magnitude of the field. So bigger the circle, bigger is the magnitude. Now let us look at x equal to d. So when x becomes equal to d, this term is anyway 1. What is essentially happening is we get cos of pi. Now cos of pi is minus 1. Yes, yeah, it's minus 1. So therefore, Hy is maximum but in the negative direction. So therefore, at this point, I will have a cross with a big circle as big as this. So the maxima is over here. The negative maxima is over here. Now what happens? What happens when x becomes equal to d by 2? In that case, this becomes cos of pi by 2 and the whole field vanishes. So somewhere in the middle, we are going to have a 0. So effectively what's going to happen? If you look at the field alignment, you will have reducing field magnitudes as a function of distance. Here you're going to have a small down arrow. It's going to now keep getting bigger, and the biggest will be over here. So positive highest reducing to 0 and now increasing to negative highest. That's it. Now let us look at what happens at z equals lambda g by 2. So when z equals lambda g by 2, let us now again see the variation along the x-axis. So when I substitute z equals lambda g by 2, what I will get is again cos of pi. So therefore, this term will become a minus 1. The rest of the analysis will stay the same, except that now what was the positive maxima here will now become the negative maxima. And what was the negative maxima over here will now become the positive maxima. So therefore, I can write this, and over here will be the negative maxima. And likewise, I can show this. Again, there will be a 0 somewhere in the middle, that is at x equals d by 2. Something of this kind. Maxima reducing to 0, then again increasing to the negative maximum. So likewise, you can now fill up the rest of the horizontal axis. What it will look like, I am just showing you the answer. Again, this one will start reducing. Something tells me that again there will be a 0 somewhere in the middle. So and likewise over here, again you will have a small dot, bigger dot, and even bigger dot. So with this you can actually fill up the rest of the arrows yourself. So what we will see, let us again not leave this problem midway. Let us look at what's going to happen over here. Let us say when x is d by 2 and z is lambda g by 4. What will happen at this point? At this point, when x is d by 2, the field will be 0. And here, because of this lambda g by 2, even this cos term would become a cos of pi by 2. So therefore, you will have a minima over here also somewhere. So somewhere over here, you may have this x term or this x direction with some non-trivial magnitude. Again, it might reduce a little bit more over here. So the direction uniformity is maintained. Something of this kind. And so on and so forth. So this would reduce and like that. So you will actually see there is a null somewhere in the middle. Now, what we can do by looking at this figure is this tells us that okay, at some given point of time, we know where the maxima and minima of the fields are lying. So this is how HY looks like. Now suppose if I can design a current probe, what I can see is that this HY is actually the tangential field. This HY is the tangential field along these two conducting boundaries. So therefore what will happen is, because this tangential magnetic field is existing along these conducting wall and dielectric boundaries, there will be a surface current. And using that current probe, I can actually measure what is the surface current, and from that I can back calculate and say, okay, now these are the points at which the fields will be maximum. This is the point at which the field will be minimum. So very similar to a transmission line, you can see that the voltage maxima, so or rather the field maxima and the minima of 0, they are separated by lambda by 4. And if you assume that this positive maxima and negative maxima are equivalent, then they are spaced at a distance of lambda by 2, where lambda is the lambda of the wave that is being guided. So once again, we are seeing that how this parallel plate waveguide using two conductors can be used to measure, or can be used to mimic the behavior of a transmission line. So what happens now? We have solved for what the magnetic field looks like. Now it's time to look at the electric field. So the electric field equations we have already written. So what were they? So we have to now look at the magnitude of the electric field. So we had written that the Ex is this. Ex and Ey we had already got. Let's not write them all over again. We have got the expressions for Ex and Ey. Now, the net electric field will be ideally a vector addition of these two. So, if I now only want to look at the magnitude, what I can do is look at the magnitude squared. So I can say the E square is nothing but the magnitude squared sum of the two components. So now that would be something of this kind. So let's write them down. I think this is it. Now, this is not the complete picture. There is some phase difference also between the Ex and Ey components, because as you can see, there is indeed a phase difference. So what is that phase difference? What is that phase difference? That phase difference, let us say, since I am now considering that my Z is the horizontal axis and X is the vertical axis, I can actually measure a phase difference and call it some phi. So let me say the phase difference between Ex, sorry, this will be Ez. This is Ez, not Ey. Let's call it as some phi that is that is nothing but, or rather I can say, the phi is nothing but the tan inverse of the vertical component by the horizontal component. So the vertical component is Ex, the horizontal component is Ez. So if you look at this, then you can easily see that this is nothing but tan inverse of this. I am dividing x by z, so this will become a reciprocal. So the beta so this will be times cot is 1 by tan. We are doing cos by sine, so we will get a cot of 2 pi z by lambda g. I think that's about it. So now what will happen is you're going to get something which is not so easy. You have to calculate the magnitude as well as the phase and then apply. So definitely the fields are not going to be all that linear, or rather all that sort of conformal to one plane or one axis. Why? Because if you remember, inside the parallel plane waveguide, when the intrinsic wave was incident, we had said that this is the magnetic field along the y-axis. So this was Hy, and the electric field was something of this kind. So as you can see, the electric field has the Ex and Ez component, which can be broken up like this. This is Ex and this is Ez. So therefore the resultant vector, which is a combination of both Ex and Ez, that is this will have some kind of a oblique arrangement. So solving that would take considerable amount of time. You can do that again in a similar way what we did for x equal to 0. You can do that for, this is z equal to x is equal to 0 and z equal to 0 both. This is the z direction and this is the x direction, and this is x equals d, and this is z equals lambda g by 4. So let us look at certain points in this waveguide. What will happen again at this point, x equal to 0, z equal to 0. So the moment you have x equal to 0 and z equal to 0, you substitute this over here. This field will vanish and this field will become maximum. So then which way will the field now be aligned? Over here. The field will be aligned somewhere. Obviously we are looking, since only Ex will remain, it will be aligned somewhere like this. What about the phase? What about the phase? So when x is 0 and z is 0, we have a cot of 0 which is, what is cot of 0? Cot of 0 is infinite. So tan inverse of infinite is pi by 2. So the phase is pi by 2. That's a given because this field is dying out. And over here, this field you can take it in the positive direction. So you will get a maximum field at x equal to 0, z equal to 0, and it will keep reducing in this direction. So I am marking the arrows now. So the longer the arrow, the stronger is the field. So what about when x equals d? So again, when z is 0, and x equals d, again this second term will vanish, Ez. So what will now happen is that over here, when x becomes equal to d, I will have a cos pi. And cos pi will give me 1 but with a negative sign, and this will continue to be 1. So again, what I will have is the phase is pi by 2, but the electric field will now be maximum with a minus sign. So therefore, this electric field will sort of look at in the negative x direction. So again, the maximum will be here, and then it will start reducing with smaller and smaller arrows. And somewhere in the middle, that is at x equals d by 2, the electric field will die down. So the rest of the analysis of the middle of the waveguide is slightly complicated, and you can do it as an exercise. So I leave you with this with this exercise and invite you to try it out to see what is the field look like at lambda by 2. Let's have it as lambda by 2. You can see that it will look like it will obey some very similar properties. So now this is one way through which we can analyze the fields which are inside the waveguide. With that, let us stop here. Thank you.